All right, everyone. This is 3.3. So we introduced the solubility product constant, which we've kind of already explored a little bit with the lab. Before you start this, can you pause the video and just try the warm-up on page 189? A few questions there just to get your brain thinking about some concepts, and then start the video once you've completed that warm-up. So let's look at the question number 1, define the solubility. So we've talked about this already in 3.1. So it's the maximum amount of a solute that can dissolve in a given volume of solvent, right? So maximum amount of solute that can dissolve in a given volume of solvent. And we have to remember that the solubility is specific for a particular temperature, and the solubility of a substance would change with a change in temperature. Second one, what is a product? Well, hopefully we remember a little mathematical terminology. A product simply means two numbers that are multiplied together, or two or more numbers that are multiplied together. And then finally, a constant represents a number that does not change, right? So in this unit, we're looking at what is called the KSP, which is the solubility product constant, right? And you've already started learning to calculate those in the lab. So if we look at question number 2, it says write a balanced dissociation equation for lead to chloride. So we have to pay close attention to the difference in the terms dissociation and precipitation, right? So with respect to a dissociation equation, we're starting with the compound and it's dissociating into its ions, right? Paying attention to the fact that we get 2 chloride ions when 1 lead chloride dissociates. So that's our dissociation equation. And then question B says, calculate the molar solubility of the lead chloride at this temperature. So if we look at dimensional analysis, we've got 4.4 grams per liter. We want to get rid of those grams and get into moles per liter. So in terms of moles per liter, we're going to multiply by the inverse of the molar mass. Grams will cancel with grams, and the molar mass of lead chloride is 278.27. So you should have come up with 0.016 moles per liter. The last question says, calculate the concentration of each ion in a saturated solution of lead-2 chloride. So again, going from the balanced chemical equation here, we've calculated that the molar solubility of lead chloride, right? So molar solubility of lead chloride is equal to 0.016 moles per liter. So that's what we've got in terms of the molar solubility. That means when this dissociates, we're going to get 1 lead-2 plus for every 1 PbCl2, but we're going to get twice as many chloride ions. So that gives us double the concentration of chloride ions. So we've got the ion concentration from the molar solubility. So I just wanted to show you the visual of thinking about these solutions from the lab and re-emphasizing this idea of solubility. So if we sort of play this and look at our silver bromide, so if you see in the top right over here, what I've tried to do is just add enough of the silver bromide where we have no precipitate forming. And if you remember, I tried it in the lab, I believe it was right around this 44, 43, 44 number of dissolved ions. And so you can see we don't have any precipitate. So this idea of solubility is that it's the amount that can actually dissolve the moment before you reach a saturated solution, right? And so this is the molar solubility of silver bromide. You've calculated it already in the lab. If I were to add just a tiny bit more, right, we'll see that we'll have that precipitate down at the bottom, and no more of that precipitate will dissolve, and we could see that with the dissolved amount of silver and bromide in the solution remains constant. We were at a saturated solution, and so the molar solubility is based on the amount of that silver bromide that could be dissolved in a given volume of solution, right? So where we go in this part of the chapter is looking at the KSP, solubility product constant. So from this dissociation reaction, we can see that the KSP, which is similar to KEQ that we started to learn about in chapter 2, we just simply refer to it as a KSP for solubility product, right? Why we have solubility product? Because remember, we're multiplying the concentration of the products, so the products being Pb2 plus times the concentration of chloride minus squared. Now, when we learned equilibrium in chapter 2, it's the concentration of the products over the concentration of the reactants. The reactant in this case would be PbCl2. Although it shows here that it's aqueous, we see that in a saturated solution, we have a solid that remains. And so we don't use solids or liquids in the equilibrium calculation. So this would disappear, and we would just be left with the product between the two ion concentrations, still raised to the power of any coefficients. Let's look at some examples here. If you turn to page 190 and have a look at the quick check. So the question, first question on the quick check says, write an equation to represent the equilibrium present in a saturated solution. So the first one is strontium carbonate. All right. And so we're writing the equilibrium present in a saturated solution. So therefore, our formula for strontium carbonate would be SrCO3. It's a saturated solution, so we've got solid with our dissociation equilibrium going to the right, producing strontium ions, aqueous, plus carbonate ions. And notice the charges are present. And we've got the dissociation. I'll do B as well. So let's look at magnesium hydroxide. So we have magnesium hydroxide, which is also known as milk of magnesia. So when you had an upset tummy and you drank that chalky, pasty stuff, that's magnesium hydroxide. Make your upset tummy go away. So you get Mg2 plus hydroxide ions. Notice how the hydroxide ions are a -1, but the Mg is 2 plus, and you've got 2 hydroxide ions that are produced for each magnesium hydroxide. So now we would look at our KSP expressions. So for number 2, it says for each equilibria above, write the corresponding KSP next to it. So I kind of run out of space here a little bit, but for I'll do this one up above. But the KSP for the first one would be equal to the concentration of strontium 2 plus times the concentration of carbonate. And that's the KSP expression for the first dissociation equilibrium. And for the second one, we would have the KSP equal to concentration of magnesium 2 plus times the concentration of OH minus all squared. Okay, I'd like you to tackle number 3. All right, pause the video, tackle number 3, and then we'll discuss the answer. If you glanced just above on page 190, just above the quick check, you see a little beige or shaded box, and it tells you exactly just what we talked about. maximum amount of solute, right? So molar solubility, maximum amount of solute that can dissolve in a given volume of solvent. Whereas KSP is the product of the ion concentrations raised to the power of their coefficients. And it's important to distinguish between the two, right? One is a specific amount with units of moles per liter or grams per liter or grams per 100 mil. And the other tells us a little bit more about the nature of the salt, the specific solubility or insolubility. So if you remember in chapter 2 when we talked about KEQ, and when we calculate a value of KEQ and saw that if the KEQ was, say, greater than 1, it would tell us that, products are favored at equilibrium, right? Meaning that there's likely more concentration of products at equilibrium than there is reactants. And if it was less than 1, the opposite would be true. If the KEQ was less than 1, that would tell us that reactants are favored. And so there's more reactants at equilibrium than there is products. So what we'll see here when we're talking about KSPs is KSPs are very, very small, right? They're of the magnitude times 10 to the minus 4 and smaller, right? And this is telling us that the types of compounds that we're dealing with really don't dissociate very much, right? If the product of their concentrations is very small, it means that the concentration of ions in solution is very small, right? So I'll flash through these next slides fairly quickly because it's a lot of review. Dissolving of a salt, right? A salt is an ionic compound, so we talked about that before, generally composed of a cation bonded to an anion, right? And in the image shown, right, is just how when we dump that solid into water, where water is the solvent, those ions will begin to separate as water begins the process of dissolving. Just like we saw in the PhET simulation, at first, everything is going to be moving in the direction of dissolving, right? So these ions are separating from solution and the process is moving towards dissociation. But as we continue to add more and more, eventually we're going to find that we've got ions that are recrystallizing as the surface of the solid provides a place for some ions to attach. And eventually we reach that point of equilibrium in which there continues to be ions that dissociate and separate from the crystal at the same time as ions attach to the crystal. And we've got equilibrium because the rate of those reactions are equal, right? The rate of dissociation is equal to the rate of precipitation. And here it shows a better picture, which we've looked at before in terms of how water acts as the solvent, the polarity of it, the negative ions of oxygen, or sorry, the partially negative charge of oxygen will attract the positive ion in the solution, and vice versa, the slightly positive end of the hydrogens in the water will attract the anion of the solution, forming what we call a sphere of hydration, right? Dissolving the substance. Again, solubility product constant. If you just want to know if a compound is soluble or has low solubility, you can use the table that we've been looking at, right? If I want to know if I combine, let's say, calcium and hydroxide ions, I can look at the chart and know whether those have a low solubility or whether they're very soluble and have an idea about their general solubility. But if you want to start comparing the relative solubilities of two compounds, we need something more exact. And that more exact is the nature of the KSP. So we've got this constant in which we can compare, right? So without giving a specific example, if I had, let's say, salt number 1, that had a KSP equal to 2.3 times 10 to the negative 4 versus salt number 2 that had a KSP of, let's say, 5.6 times 10 to the negative 8, right? Which salt is more soluble, and how do you know? So pause the video for a second, give it some thought. Which salt is more soluble? Well, if you thought about this, 2.3 times 10 to the minus 4 is much greater than 5.6 times 10 to the negative 8, since they are products of their ion concentration. If this number is greater than this number, it means that there's more ions in solution, and therefore it's more soluble, right? So here's the general form that we've looked at, and we should have already had practice with in the lab. If we've got our equilibrium set up as such, then our KSP would correspond to the product of the concentrations raised to their coefficients. In this case, the M has no coefficient or 1, therefore it's got no exponent or an exponent of 1. And over here, if this is N, then it's raised to the coefficient of N for whatever number represents this particular combination of ions in the salt. Solids and liquids, remember, are not included in equilibrium expressions. And when I looked at marking, a lot of quizzes where we were practicing writing KEQs, students are getting in the habit of just writing whatever products are shown in the reaction over the reactants. But we really have to pay attention to the fact that the states dictate whether or not you're part of the equilibrium constant expression. So solids and liquids, because they are pure substances, this is the key, right? Because they're pure substances, their concentrations don't change when you add more or take some of them out, right? Think of it as density. If I had a block of gold that had a density of 20 grams per centimeter cubed, right? So just imagine, I'll erase some of this so I can draw, right? So if I had this block of gold, and gold has a density of 20 grams per centimeter cubed, if I cut this gold in half, right? And remember, concentration has to be the amount of something in a given volume of space, right? So in this case, the amount is the mass and the volume is centimeters cubed, but it could easily be liters or milliliters or whatever. So when we're calculating equilibrium constants, we're looking at concentration, specifically concentration, because that's what we defined when we looked at the rates of reaction and how rates are dependent on concentrations, that it was concentrations that would affect the equilibrium constant. So if I divide this block of gold into two equal halves, well, whether they're equal or not equal, the density of this substance doesn't change. It's still 20 grams per centimeter cubed, right? Remember, density is equal to mass over volume. In this case, if I cut the block in half, well, I'm dividing the mass in half, but I'm also dividing the volume in half. So it's half the amount of space. So if I divide top and bottom by 2, I'm really just dividing by 1. The densities stay the exact same, and I haven't changed the concentration. So because solids and liquids are pure substances and their concentrations don't change, they're not part of the equilibrium expression. So we don't see the MXN as part of the equation. Okay, those definitions just repeated, right? We got to get familiar with them. Molar solubility is specific to moles per liter, whereas solubility can be given in any number of units, typically grams per liter. Sometimes grams per 100 mils is fairly common, right? When we're talking about KSPs, okay, KSPs are calculated using molar solubility. So those constants would be different if you're using different units. So we're using moles per liter. And one thing that's important to recognize is that you can just as equally use molar solubility to determine the KSP. You can also use the KSP to determine molar solubility. So here's where we get into the problems of calculating, much like we did in chapter 2, with looking at different amounts and using the amounts at equilibrium to either calculate the KSP or being given the KSP and having to calculate the amounts of ions in solution based on the KSP. Okay, when you're solving problems with KSP, you want to make sure you've got the equilibrium equation balanced, right? So much like chapter 2, you've got to start with a balanced equilibrium equation. Then you want to make sure you've written out the solubility product expression. So this is our KSP, right, times A, or whatever your substance is. So if I had, A, B dissolving into A plus B minus, then our solubility product is A plus concentration times B minus. So we have that to start with. And then determine what you do and don't know from the question. What information are they giving you, and what is it that you have to solve? So let's have a look at practice problems 3.1. All right. This is on page 192. All right. And so what I want you to do is try question number 1. So pause the video, page 192, question number 1. Pause the video and then restart the video for the solution. Okay, in the first question on page 192, calculate the KSP for each of the following. So starting with calcium carbonate, it has a molar solubility of 6.1 times 10 to the minus 5. What they're wanting us to calculate is KSP. So we have to calculate the KSP. So therefore, somehow we must know these concentrations. But since it gives us the molar solubility, 6.1 times 10 to the minus 5, then we can figure out these concentrations of calcium and carbonate, because this represents the maximum amount of that calcium carbonate that can dissolve in solution. So therefore, when this dissolves, you're going to get 1 calcium and 1 carbonate. So it's all 1 to 1. Therefore, the concentration of calcium is 6.1 times 10 to the minus 5. And carbonate is also 6.1 times 10 to the minus 5. So therefore, to calculate the KSP, we can simply substitute in our concentrations 6.1 times 10 to the minus 5 times 6.1 times 10 to the minus 5, and simply square those numbers to get the KSP. So this should give you 3.7 times 10 to the negative 9. And again, when we're looking at the size of this, the magnitude of the KSP is telling us it's very low solubility. So why don't you try number 1C and try number 3, all right? And we'll go over both of these in class and as well do more practice problems. Keep in mind with number 1C that it's giving you the molar solubility in grams per liter. But remember, when we do KSP calculations, we want things to be in moles per liter, the molar solubility, right? Okay, try 1C and number 3. Enjoy the rest of the weekend. See you on Monday.